Welcome to another great O'Reilly webcast. My name is Yasmina Greco. I'm with O'Reilly Media, and I will be your host for today's webcast. Today, folks, we have Joseph Howse with us, and he is going to talk to you about training intelligent camera systems with Python and OpenCV. Joseph has 4 first-rate cats, yet if his books sell well, he could build a menagerie fit for a pharaoh. When he's not writing books or grooming cats, Joseph is working to grow the augmented reality industry by providing software development and training services through his company, Numbist Media. Folks, Joseph is also the author of a few best-selling books from PAC Publishing, OpenCV Computer Vision with Python, as well as Android Application Programming with OpenCV, and his latest brand new book with PAC Publishing is OpenCV for Secret Agents. Folks, we're very excited to have Joseph with us today to present this webcast for you all. As we get the event started, I'd like to go over a little housekeeping to help you get the most out of today's webcast. First, you'll want to open your group chat widget if you haven't already done so. This is where we can interact with each other during the event and where you can submit your questions for Joseph. We find that our audience usually has a lot of good knowledge to share, so we encourage you all to chat freely during the event. However, if you have questions for Joseph, please preface them with a capital letter Q so we know that they're for him and we can make sure we see it for Q&A. You can also open, move, and resize any of the other widgets. If you would like to tweet from the Twitter widget today, you might need to give it permission to access your account. The Twitter widget will automatically append the event's hashtag to your tweet so you don't have to. And today, folks, we have 2 hashtags, Python and OpenCV, all one word. If you have any trouble with the webcast, please take a look at your help widget. If you continue to have trouble, just post it in the group chat and one of our staff will help you right away. If you have choppy audio or stalled visuals, please try refreshing your window. And remember, the best thing you can do for a good audio stream is to close any apps that could interfere. People always ask, so we'd like you to know we are recording today's webcast, and we will have the archive ready usually within 48 hours. And folks, at this time, it is my pleasure to turn the program over to Joseph for his presentation. Hello, Joseph.
Hi. Thanks, Yasmina. Hi, everybody, and thanks for tuning in. Today, we're going to build a set of software that analyzes photos and real-time camera input for the purpose of detecting and recognizing the faces of humans and cats. When I say detection, I mean that we want to locate instances of some class of real-world object in an image. For example, if we draw a rectangle around human faces, that's a detection task. Recognition means that we want to refine our classification further. For example, we might want to say, this face that we detected is a male face, or this face is Joe's face. Detection and recognition are often done in combination with tracking, which means that we look at a series of camera frames and we want to conclude that this face moved from here to here. But today we focus on detection and recognition. We're working with Python, a scripting language that should be relatively readable even if you are new to it, and a computer vision library called OpenCV. OpenCV is available in bindings for several languages, and the Python bindings represent images as NumPy arrays. NumPy is a library for matrix math, If you're at all familiar with MATLAB, NumPy provides a similar syntax for matrix math within Python. And finally, we'll be working with the WX library for user interfaces. These libraries take a bit of time to set up, so I've included an appendix to these slides with more detailed instructions. But to follow along, you might want to go to either of the links below to get the source files for the project we'll be discussing. It's part of my upcoming book, OpenCV for Secret Agents. We'll be discussing a subset of the project that lets you train detectors and recognizers for people and cats. The whole project is to set up an alarm that's triggered by some person or cat's face. If you have Git set up on your system, go to the first link for instructions on checking out a Git repository. If not, go to the second link to just grab a zip download of the project. As well as the source code, we work with 3 big databases of images that are developed as part of university research projects, or in one case, a Microsoft research project. They include images of human faces, images of cat faces, and images of other things such as backgrounds. The project includes a download script for these files. The download script is written for Unix. If you're on another type of system, you can just open it up and see the appropriate URLs to download. Now, in any computer vision application, the first thing you need to do is acquire images. OpenCV provides a class called Video Capture, which you can instantiate with either a camera ID, 0 for your system's default camera, or with the file name of a video file. With an instance of this class, we can call a read method to get an image and a flag indicating whether reading the image succeeded. If you're not familiar with Python, note that functions can have multiple return values, which are comma separated. Similarly, for getting an image from a still image file on disk, we have the imread and imwrite functions in OpenCV. OpenCV contains some GUI functionality of its own, but it's very basic, so it's better to integrate with a third-party GUI library such as WX. There are 2 main integration considerations that I'd like to highlight. You want to run your camera capture code and your image processing code, all the OpenCV stuff, on a background thread. Otherwise, you're going to stall the main thread where your user interface is running. You can achieve this using Python's standard thread class, and in WX using a function called callAfter, which you run from your background thread when you want to notify the main thread to run something like updating a displayed image. Secondly, you need to convert your images from the NumPy array format that OpenCV uses to whatever image format is used by your GUI library. In WX, it's called static bitmap, and there are helper functions for generating a static bitmap from an array of data. Let's have a quick look at some demo code where we capture and display images. So this class Interactive Recognizer is the core of our project. It's used to capture and display images and interactively train a recognizer for people's or cats' faces. In our initializer for the class, we instantiate a video capture, and we get the width and height of the camera capture in pixels so that we can set the window size appropriately. You can also set those widths and heights if you have a particular video resolution that you want. And at the end of this initializer, we start a background thread running a function called runCaptureLoop. In that function, we're just capturing a series of frames. If we capture a frame successfully, we send it along to another function called detect and recognize, which we're going to discuss later. That's where our real computer vision work is done. We flip the image left to right for display so that it's more like looking in a mirror. And then on the main thread, we call a function called showImage. The implementation of showImage just does some conversion of image formats, and I'll leave you to have a look at that, or if you have questions about it, you can ask me in the Q&A. Now, our first computer vision task is going to be detecting a human face. And OpenCV supports two types of detectors that are good for detecting faces and other objects. The first is called Howse Cascades. It's the more reliable model of the two. And it works by looking at certain geometric rectangular transitions in the image. If you think about a face in a very abstract way, you can think that it has some dark rectangles for the eyebrows, for the eyes, for the mouth, and maybe some brighter rectangles on the nose or the cheeks or other large areas of skin. The other model is called local binary patterns, or LBP. It's faster, but not quite as reliable. And it works by detecting transitions from dark to light in any direction rather than the particular geometric patterns that Howse Cascades look for. Both of these models can detect faces at multiple scales. So they might first do a search for a face that's around 100 pixels and then around 115 and so on. Both models store their data, their definition of what a face is or what some other object is, in an XML file. And they both assume a particular orientation for a face. It needs to be upright. So if I turn my head sideways, it would no longer be recognized by a detector that's trained for upright faces. If you have an asymmetrical object, such as a face seen in profile, or a cat's face that might have markings on one side but not another, then mirrored objects will not match a detector that was trained with non-mirrored objects. OpenCV comes with a lot of XML files that are pre-trained for certain detectors. Many of these relate to human faces, a face seen from the front, a face seen in profile, parts of a face such as eyes. Others deal with larger areas of the human body. And there are a couple of miscellaneous detectors, one for silverware, knife, fork, spoon, and another one for Russian license plates. OpenCV has a lot of developers in Russia. The basic usage of these detector files is simple. We instantiate a class called Cascade Classifier, passing it the path to a detector. And we call a function called detect multiscale, passing it an image. We get back a list of rectangles indicating the regions of the image that contain a face, or are believed to contain a face. These rectangles are in the format XY width height. Detect multiscale has a number of important optional arguments. I've listed the link for the documentation there, and we're also going to look at a few of them now in a code sample. So in our detect and recognize method, an interactive recognizer, the first thing we do is convert the captured image to grayscale and apply a kind of contrast adjustment called equalization. If you're familiar with Photoshop or GIMP, this is the same equalization filter as in those image editing programs. It stretches the contrast of the image so that there's definitely going to be some pure black and some pure white and a more or less even distribution of gray tones in between. When doing detection and recognition, you always want to convert to grayscale and equalize, because that will help you eliminate differences that are due to different lighting, and in people's faces it will also help you eliminate differences between people's skin tone. Now, we run our detect multiscale function with this equalized image and some optional arguments. We can specify a minimum size of face that we're looking for in pixels. For example, we could give it 40 by 40 as a minimum size. Or it might be bigger if we know the user is going to be close to the webcam. We can specify also a maximum size in the same way, and a scale factor. The scale factor is the step between different face sizes that we're looking for. So if at one step we look for a face 100 pixels big, and the next step we look for a face 115 pixels big, a approximately, then we could set this value to 1.15. Our default for it in this class is 1.3. You don't have to worry about missing too many faces just because you didn't search every pixel size. It's not that exact. Now, when OpenCV does detection, it can detect overlapping faces, and overlapping detections usually are in reality the same face. If you look at one region of an image that's a face, and then you shift the rectangle a little bit over, that region probably looks like a face too. These overlapping detections are called neighbors, and we can specify a minimum number of neighbors that we expect to see in something that's really a face. And then we merge all those neighbors together into one rectangle, or OpenCV does that for us automatically. I believe our default value here is 4. So we have to detect a face 4 times to be confident that it's a face. This last argument here specifies some other optimizations. There are a number of mutually exclusive optimizations available. Through testing, I have found that the best optimization is almost always one called CV har scale image, which applies some low-level optimizations to the way that OpenCV scales the image between a search at one size and a search at another. Having detected these rectangles, we draw a box around them. Here's an example. This is a little script that makes an instance of Interactive Recognizer and runs it with a pre-built cascade for human faces. So you should see my face here with a green box drawn around it. And that is face detection using one of the detectors pre-built for us in OpenCV. But what if we want to detect something and the OpenCV team didn't already provide us with an XML file for that type of object? In that case, we have to train our own XML file. And OpenCV comes with 2 command line tools for doing that. Among other arguments, these command line tools require some text files that list negative training images. For example, things that are not the faces of cats, and positive training images, things that are the faces of cats. I have in the project a little script that demonstrates usage of these command line tools. The Unix version is called train.sh. There's a Windows version as well called train.bat. At the start, we define some paths to files that are inputs and outputs of these tools. And we count the length of the positive and negative lists of training images. These sets of training images need to be quite big. In our example with cats, we're going to deal with about 10,000 positive training images and 5,000 negative training images. Hi, sorry, there was a slight disconnection there. Everybody with me?
Yes.
Good. So if you can still see the code here, the first command line tool, OpenCV create samples, takes a list of positive training images and negative training images as inputs. These are the paths to the text files. And we give it a path where we want to output a binary version of those lists of training images. We also tell it the number of positive training images. The second command line tool, OpenCV train cascade, takes those lists again, and it outputs an XML file. We specify the path to the XML file. We also specify the manner in which we want to train this cascade in multiple stages. Our detector ends up applying not just one test for whether the object in the image is a cat, but a series of tests, and each test is called a stage. Each stage is trained with a slightly different subset of all our training images, so that we get some variations in our test, and we're not relying overly on just one sample of the training data. So in this case, we want to specify a number of positive and negative training images per stage that is less than the total. It must be less than the total, or OpenCV will complain. And as a rule of thumb, we're using 90% of the total. We specify a number of stages. Here we're using 15, and a minimum hit rate or accuracy at each stage. We're specifying 99.9. Making it higher takes longer to train and makes the model fit the training data more tightly. But you don't want it to be such a tight fit that you end up with a model that can't extrapolate beyond the training data. So 99.9 is sometimes recommended as a rule of thumb. And we get an XML file as output and copy it to some location that we want. This XML file can be used with our interactive recognizer class. So just a slight variation on the code we used for human face recognition turns this into a cat face detector and recognizer instead. And we have a couple cats in the room, and I'm going to try to grab one as a participant. So bear with me for one moment. Now, you saw that the cat's face was detected. You might have also seen that there were some false detections of my human face as a cat face. The cat face detector is a little less accurate than the human face detector that comes with OpenCV. And one way of working around that inaccuracy is to run both the human face detector and the cat face detector at the same time. And if something is detected as a human face, you can then rule out the possibility that it's a cat face. The human face detector is more accurate. In the sample code, there is another class that we're not going to go into in detail today called Angora Blue. That's the class that sets off an alarm, an email alert, when it sees a specific human or cat. And it contains the technique of first detecting human faces and then ruling out the possibility that it's a cat face. Now, the real work in training our own cat detector comes in preparing the training images. All the negative training images need to be converted to grayscale and equalized. But we need to do a little more for the positive training images. We also need to straighten them and crop them so that the eyes are always level and the eyes are at a standard height in the image. This is really essential. I mentioned earlier that OpenCV's detection models don't work with images in different rotations from the training images. So we've got to standardize on one orientation or you'll get poor detection results. Now, fortunately, the set of cat faces that we're using from Microsoft Research comes with some text files for each image that describe the location of certain points of interest. These files were all generated by a human being. A person looked at each image and determined where the cat's eyes were, where the base of the ears on each side was, and so on. So there's a lot of manual work in locating these points of interest in training images. For our purposes, we somewhat arbitrarily define a cat face to be as wide and as tall as the space between the base of the ears. And we level it according to the eyes. We center the eyes horizontally and place them at 10% above the center line vertically. That gives us training images like this. So this fellow on the left gets rotated and cropped to give us the image on the right. He's saying, can I has Arctangent in reference to the Arctangent function in many programming languages. Now, this next training image is of a cat with his ears sticking far out beyond the rest of the head. I thought you might have been wondering why we would define a cat face in a way that excludes most of the ears. And it's a good question because the triangular ears are a very distinctive feature of a cat. However, if we were to draw a rectangle around this guy's ears, we would be including a lot of background. And in some images, that would be bright background. In other images, it would be dark. In some, it would be flat color. In other images, it would be textured. And it would just mess up and confuse our training of the definition of a cat face. So you want to be careful about excluding background. We have in the project quite a lawn script called describe.py that generates the lists of training images and applies the necessary pre-processing. It does this by iterating over negative training images in certain directories and positive training images in others. It saves out equalized versions of the negative training images. And for the positive training images, it also applies rotation using ATAN2 to calculate an angle between the eyes, generating a definition of the necessary rotation using an OpenCV function called getRotationMatrix2D, and applying that rotation using another OpenCV function called Warpifying. We then crop. NumPy arrays, like Python's standard lists, support a slicing notation. So this means we're cutting out some portion of the image from y to y plus height and x to x plus width. Note that y, or columns, is the first index. X, or rows, is the second index. So be careful not to mix up the order. Now, that covers the detection functionality in our app. But we also want to recognize specific human beings or specific cats. Before we launch into that discussion, I'll do a demo of our GUI features for recognition. I'm sorry, I'm running the cat face recognizer there. We want the human face recognizer. So there I am. And when my face is highlighted, we have a text box here where I can type in a name and click Add to Model to indicate that this face we're currently seeing is Joe's face. And based on previously added images, our recognition model is saying that this looks more like Joe than like other people we have seen before. It also gives a value called distance, which is a measure of dissimilarity between the current image and images in the set of training images. So if we click Add to Model, we will see that the distance value went down a lot because we just added an image that's very similar to the one on screen. And those are the features we are wanting to discuss now. OpenCV supports 3 types of recognition models that are tailored to faces. They were originally designed with faces in mind, but you can apply them to other types of objects too. 2 of these models are quite similar to each other. They are called eigenfaces and Fisher faces. They rely on building up a statistical model of the average face that we have seen and the differences that we statistically expect to see from the average face in the face of a specific person. For example, our model might say that Joe has dark mustache pixels more than the average person does. The third model is our old friend local binary patterns, the same model as in detection. And it is faster but not quite as reliable. Its big advantage is that it isn't building up any statistical model of the average face and differences from the average. It just learns from new faces one at a time. And so it's very appropriate for an application where we want to train a recognizer in real time, like our app here. All these models, again, store their data in XML files, and they assume a particular orientation of the face. You won't get good results if the face is upside down, or if a cat with asymmetrical face coloring is seen in a mirror. The API for these 3 types of recognizers is mostly the same. We create an instance using OpenCV functions called create LBPH recognizer, or create Fisher face recognizer, or create eigenface recognizer. We train the recognizer by passing it an array of training images and integers that are used as IDs for that face. For example, if we have 2 faces that are Joe and 2 that are Sam, we might say Joe is 0 and Sam is 1. When we get an image from the camera and we want to identify that person, we pass that image to a method called predict. And that gives us 2 return values, the ID number and that distance measure that we discussed before. With LBPH recognizers only, we can add more training images and labels later. We can save to an XML file and load from an XML file. And once again, there's a demonstration of a recognizer class. in our interactive recognizer code. When a user hits that Add to Model button, either the train or update method of the recognizer is used. When a new face is seen, we pass it to the recognizer, and get back a label and the distance that we use to update our text at the bottom. So I'll just quickly run that app again to refresh everyone's memory of what it does. And it shows that this is Joe and this is the distance. And we can update it by entering text and hitting that button. So that is the end of our whirlwind tour of face detection and recognition in OpenCV with an emphasis on human and cat faces. You can potentially apply the same techniques to other animal faces and things that aren't faces. If you're interested in these and other OpenCV topics, please consider having a look at my OpenCV books. There's an intro to OpenCV Python and an intro to OpenCV Android currently out. The more advanced book, OpenCV for Secret Agents, which contains a bunch of weird projects using lots of sensors and gadgets with Python and Raspberry Pi and Android. It's coming out in a few months, and meanwhile you can pre-order and get beta access to it. Some projects in there include classifying real estate as to whether it's luxury real estate that would be suitable for a globe-trotting secret agent to stay in, or alarms set off by cat faces or human faces, gesture control, some projects dealing with cars and detecting obstacles, a project dealing with detecting a person's heartbeat from just an image of their skin, and other interesting things. There are lots of other good OpenCV books as well. These are two that are always on my desk, dealing with the C++ API, mostly. If you're here just to learn about cat recognition, and honestly, who isn't, then have a look at this research paper by Microsoft. It describes the detector that they built using the same data set that our demo uses, though they don't actually share their code. You'll want to check out API docs and perhaps some blogs on the web. There's a JavaScript cat detector that might interest you called KittyDar. And last, these slides include the setup appendices that will help you get started with OpenCV and related libraries on Windows, Mac, Debian Linux, or Ubuntu. So thank you again for tuning in, and I would like to open things up to questions.
Thank you so much, Joseph, for a really terrific webcast. And we have a lot of questions that have come in, as you can imagine. So folks, as you heard, we are at the Q&A portion. If you have a question for Joseph, please open your group chat widget, type it in, send it in, and we will take as many as we have time for. Okay. Joseph, I'm going to ask you, are you able to see them, or do you want me to read them out loud?
I can see them, but why don't you read them out loud?
Okay, here we go. We'll take them in the order that they came in. Let's see here. Talon would like to know, what are the dependencies for OpenCV 2.4 with respect to 2.3?
As far as I'm aware, the dependencies are mostly the same. It's a recompile of OpenCV that you'll need to do. I believe 2.4 might have added support for some newer versions of codecs, video codecs, compared to 2.3, but mostly the same dependencies.
Thank you. Charles would like to know, what's the LBP versus HAR reliability in terms of false positives, false negatives?
It varies a lot depending on the resolution of the subject. So the difference between HAR and LBP for a close-up subject with a mid-resolution or high-resolution camera is negligible. But the HAR will do a lot better if you're trying to detect smaller resolution faces, either because the faces are more distant or because your image resolution is low.
Thank you. Next question from Earl. Are there any licensing issues with using OpenCV in a commercial app?
No, it's a liberal open source license. A few of the algorithms implemented in OpenCV have patent issues associated with them, but none of the ones we discussed today do. The most notable patented algorithm in there is one called SURF, which is for tracking, locating something in 3D.
Thank you. Aaron would like to know, does your new book, OpenCV for Secret Agents, focus mostly on Python or other languages as well?
It's a combination of Python and Java for Android. It's about 60% Python, 40% Android.
Thank you. Let's see here. Charles is asking, how similar should the negative samples be?
The negative samples should be a wide variety of things. For example, we're using a big data set of negative images that includes cars, city landscapes, rooms indoors, human faces, and we add an extra set of human faces to the negative training images because human faces look quite similar to cat faces. So you should include in the negative training images a big miscellaneous set of things, plus things that maybe look kind of similar to the positive images, but aren't positive images.
Thank you. Steve has a question. He would like to know, if you also want to detect cats in profile, left and right, would you need to train for each of those perspectives?
You would need to train a separate profile detector. With profiles in human faces, what you normally do is train either the left or the right, and then you flip your image from the camera to try it from both sides. But, that would work with cat detection, too. but for recognizing a specific cat, you can't assume a symmetrical face. So you might need to train a recognizer with both the actual left side and the actual right side.
Thank you. Let's see. Question from Philip. Can you chain detection for, say, human faces and cat faces, or do these require two entirely separate detection passes?
Separate passes.
Great. Let's see. Next question here from Sue. What is an ideal resolution for the sample images versus the images passed through the classifier?
That is a good question. The training images can be a pretty small resolution, especially for a recognizer. They should be a small resolution. The reason is when you scale down the images, you can eliminate things like camera noise that are going to get in the way of recognizing a specific individual. When scaling the training images, you want to use an interpolation method called area interpolation, which reduces noise. So you can see some examples of that in the describe.py file.
Thank you. All right, a couple more questions here. Steve would like to know, are there issues with performance in using Python for multiple detections?
The C++ API is the most optimized. However, NumPy, which is the basis of the Python API, is also a well-optimized math library. Underneath, NumPy is using C arrays, not standard Python lists or another Python data structure, which would be very inefficient. So optimization of the Python API is pretty good.
Thank you. Let's see. Question from Jack. I'm sorry. Yep. Any processing suggestions if it's colors you're looking for? Or pre-processing suggestions, sorry.
You can do detection of a specific color as well, but it's not really what these models are designed for. So if you're trying to do something like detecting a red ball, for example, there are simpler models that will run much faster. In the example of a ball, there's a function called Howse detector, HOUGH, which will get you circles, and then you can find the average color in that circle, something like that.
Great. A couple more questions here. Dean would like to know, do you have any experience interfacing OpenCV with 3D data images generated using a Kinect sensor?
There's a short intro to that in the introductory Python book. So yes, a little bit, and maybe follow up with me offline. Also, the question on optimal size of recognition or detection training images. Follow up with me offline if you like, because I realized the code that I thought was in describe.py is actually in another project. So follow up offline if you like.
Okay, we'll take this final question from Jack. What kind of detection is hard? As in, I have to throw a lot of hardware at it and have complex training, volume of images I want to check.
Any of the detection models we looked at today can run pretty well on any recent laptop. You can even run them on some single board computers. Raspberry Pi, for example, can do human face detection at somewhere between 5 and 10 frames per second, depending how well you optimize it.
Super. And folks, I'm just pushing out it's your URL, your numis.com website, Joseph, to folks. So if they want to follow up with you or have more questions, there's ways you can contact him there. And
yeah, I'm happy to get questions and comments that can be used to improve the upcoming book.
Super. And as we close out, we are going to say a very big thank you to you, Joseph, for spending your time with us today and for presenting an outstanding webcast. That was also a lot of fun, and for sharing your knowledge and expertise with us.
Thank you all.
Folks that attended our webcast today, we thank you for attending and hope you've benefited from it. And a big thank you to those of you that sent in questions, because having your questions really adds so much to our events, and we thank you for that. And finally, we'd like to let you all know, please open that group chat if you didn't open it before you leave. There are some links and some codes in there on Joseph's book. So we pushed out a couple URLs to his current books with O'Reilly that we have distributed on the site, the Android book and the Python Computer Vision book. As well, we pushed out a link to the Pact Publishing site so you can take a look at Joseph's brand new book, pre-order it. It's called OpenCV for Secret Agents, and all three of these books have so much in them that can really help you with your projects and your day-to-day. So please, we invite you to take advantage and take a look at them all. Folks, this will conclude today's webcast. Goodbye, everybody.